In this section, we're going to relate work to energy. Okay, we're going to relate work to energy. And we've already really done that because the unit of work is joules, and joules is a measurement of energy. So we've done this yesterday already, but this is kind of going to relate it to the concept of kinetic and potential energy. So we're going to talk about different forms of energy. We're going to use what's called the work kinetic energy theorem. And then we're going to talk about different problems with potential energy and different types of potential energy. So let's start first with a simple formula. This formula is the energy of motion. This formula talks about the energy of motion. Any of you that are athletes that have played a sport know for a fact that if you're moving, it's harder to stop you than if you're standing still. If you're standing still, if you're moving very slowly. If you're moving, as you move faster, it's harder to stop you. You have more energy. If you're bigger, it's harder to stop you. You have more energy. What is energy, in this case, a function of? M and V. M stands for? V stands for? Those two things. It makes sense logically. Again, that's why I said this chapter, a lot of it is logic. Kinetic energy is a function of mass and velocity. If you got more mass, you have more energy. If you have more velocity, you have more energy. Now, one of those is squared, so they act differently. So if you double your velocity, it's not going to double the energy, it's going to quadruple it. If you triple the velocity, it's going to increase the energy by a factor of 9 because it's squared for velocity, whereas mass is just directly related. The 1/2 is just part of the etymology of the formula. These come from a lot of calculus, these formulas, is where they come from. That's where the 1/2 comes in role. But it's just the coefficient in the front. So again, this is kinetic energy, the energy of an object in motion. It's really the simplest type of energy we're going to look at this year. If an object isn't moving, does it have kinetic energy? Because it doesn't have any what? What's the variable? Velocity. But it always has what? Everything has mass. Again, everything has mass. Even these, new theories of massless particles and stuff, we're not going to really go into that, but like when you study electrons, you assume electrons are almost massless because when compared to a neutron and a proton, the mass was insignificant, but it does have some mass. So anything we study in this class is going to be on the macro scale. Everything has mass. So if there's no energy, it just means there's no velocity. There's no velocity. So let's look at a first example here for kinetic energy. So a bowling ball moves. The bowling ball's mass is 12 kilograms. I said that right away. It doesn't say it in the problem though. So you need to know your units here. The units of mass are always given in kilograms. So right off the bat, you should either circle this or write down that M equals 12 kilograms. Okay, it's not the weight. It's not the weight. This is the bowling ball, and it moves at a velocity of 3 meters per second. And now we have you ever use those bouncy balls? You know what I'm talking about, like the super balls? Okay, they're like they're actually very, very light in mass. So 4.5 grams. And the question is, how fast must it be traveling? So if I were to specify, my AirPlay stopped working, give me a sec. If I were to specify between the bowling ball and the super ball, the bouncy ball, whatever they're called, what should I do with my variables? What should I give them? Yeah, subscripts. So maybe we'll call this mass 1 and V1 and mass 2 and V2. I forgot I paused. For football players, you think about the idea of a linebacker and a running back. A running back is usually one of the smaller guys on the field, actually. Even though they're pretty big compared to the size we are. But compared to like linebackers and defensive linemen, defensive ends, those guys are much bigger. They don't need as much velocity to stop a running back. The running back has to run pretty quick if they want to barrel through a defensive man because the defensive man has a lot more mass than the running back does. So our goal here is to find V2. So we're trying to figure out the kinetic energy of each of these and set them equal to each other. So the kinetic energy of object 1, 1/2, mass 1, V1 squared. So the kinetic energy of object 1 is going to be 1/2 times 12 times 3 squared. Half of 12 is 6. 6 times 9 is 54 joules. That's the energy of the first object. Again, that's the energy of the bowling ball only. The mass of the bowling ball is 12. The velocity of the bowling ball is 3. 1/2 times 12 times 3 squared.
Sorry, why are you squaring 3?
It's just from the formula. Go back. Here. What about the second object? What should I do when I think about the equation for the second object now? If they're going to have the same energies, what should I do, Ernest?
So it would be 54 equals 1/2, 4.5, we know what v squared is.
So we're trying to find v squared, but it's not 4.5, Ernest. Be careful.
Where you take kilograms.
Yeah, I got to move it 3 decimal spots. 0.0045. Remember, the mass was given in grams. To convert to kilograms, it's a much, much bigger unit, so the number gets smaller. By how much? By 1,000, because kilo means 1,000. So I move it 3 decimal spots. And then solve for V2. Again, why did Ernest say 54 equals and not KE equals? Yeah, we want the same energy in both objects. So we might say this to start. If you wanted to do it like this, you could say this. You could start with that. Kinetic energy of object 2 equals 1/2 m2v2 squared. But since kinetic energy of object 1 and 2 are the same, we can take this value of 54, since they're the same, and plug it in for the second object's kinetic energy. Good? George?
If they just asked for the kinetic energy of the second object, you wouldn't be able to figure it out, right?
Correct, George. Very good. You cannot figure out the kinetic energy of the second object if you didn't know it was the same as the first, obviously. Since it's the same as the first, it's 54. But without the V2 there, you can't directly find KE2. Anybody think of a quicker way to do this? Right off the bat, something that's easier to do? We did them separately, didn't we? We did KE1, and then we found that and set it equal to KE2. What could I have done right off the bat to make this problem a lot simpler and faster? A lot of you struggle with time, that's why I'm saying this. What could I have done as an alternate solution?
Couldn't you, before you plug it in, move it all over, so you have V1?
I could have solved, yeah, that's one way to do it. You could solve for V right off the bat, that works. What else? Clausa?
Couldn't you just do half of m1 times v1 squared equals half of m2 times v2 squared?
Very good. Okay, that's the solution I would approach with, because look what happens. All this is saying is the kinetic energy of the first object equals the kinetic energy of the second object. And then what happens to the 1/2s? They cancel out. They're on both sides. So this makes it a little bit quicker to go through the solution. So again, you could find the kinetic energy of the first one, set it equal to the second one, or just set the energies equal to start. Since the problem said they have to have the same energy, set the equations equal, and then simplify. Cancel, cancel. If a factor is on both sides, you can easily cancel it. So this is the first object's energy, and it's equal to the second object's energy. And now we could solve for V2 algebraically or plug in numbers. I don't care either way. It's up to you totally. If you want to plug in numbers for M1, V1, and M2, and then solve for V2. Or solve for V2 algebraically. How would I get V2 by itself? I would divide by M2. Right, I'd divide by M2, put it over here, and then take the square root. And it gets rid of the squared there. So again, divide by M2, it becomes M1 V1 squared over M2, which is this. And then you take the square root to get rid of the squared, take the square root. Please, you don't need to simplify this any further. If you wanted to, you can, but I would plug in numbers at this point. Okay, if you wanted to go crazy and do this, you can do that also. The reason I can do that is because the square root of M1 over M2 stays by itself, and the square root of V1 squared, what happens to a square and a square root? Yeah, they're inverse operations. They cancel, leaving behind V1. So you could write it like that also. But I would, if I were you, just to be simple, I'd plug in here or here. Okay, plug in one of those two locations. You don't need to algebraically simplify this all the way. Okay, if next year you decide you want to take AP Physics and you're in that class, a lot of these algebraic approaches are used. There's actually a lot of the time no numbers even given. It would say find the solution for the velocity of the second object in terms of all the other parameters. And that would be your final answer. Okay, either way, what do we get for V2? Whether we solve it here, or plugging in here, or plugging in here, or here, anywhere else, what do we get for V2 no matter what? 154? 154?
0.9.
Check it. 154.9?
You get 2400
I heard three of you say it, so I'm agreeing.
with that, square with that.
I did get 154.9. Just check your work, please. Make sure to check your work.
Oh, I got 2,400.
So do that. And then
Watch your zero. And the interesting part is that when you miss a zero and then you square root it, it's not even off by a factor of 10, so you don't recognize it right away. Normally you'd say, oh, my answer was actually just 15.4. But when you square root it, it's not going to be the same. Does that make sense? Questions so far? Quite fine. Okay. Good? All right. Let's go to the next slide. This next thing we're going to look at relates yesterday to today. Yesterday in class, what was work defined as a formula? What was work equal to yesterday? Very good. Good memory. FD cosine theta. Now, we talked about yesterday, when you give an object energy and you do work on it, it's going to make it move, right? So when I do work on this and I push it, it moves. When I let go, friction does negative work and it stops. So there is a relationship between velocity and work. That's what we're going to derive right now. So this is called the work kinetic energy theorem because it relates work to kinetic energy. Kinetic energy is motion, right? 1/2 mv squared, the previous slide we just did. Work is FD cosine theta. So I'm going to show a quick derivation of where it comes from. You don't have to repeat this ever, but I want you to be able to understand how they're related to each other, okay, and why they are, because energy and velocity are very similar. So we're going to start with our definition of work, and I put in one dimension. The reason being, I'm going to assume for now that theta is 0 degrees. So our definition of work is simply work equals FD cosine theta. If I'm only looking at work in one dimension, meaning it's only moving horizontally, theta is 0. What's the cosine of 0? 1. Good memory. So this just drops off, really. So if I'm only looking at work in one dimension, this formula becomes W equals FD. Times 1, obviously.
so that one technically it didn't say cosine. It just said that.
Yeah, if a force is ever applied horizontally, you just have to use FD because it's cosine of 0, which drops off. Now, after that, what we want to do is think about the fact that we have a definition for force. What did Newton's second law tell us? F equals ma. So replace that. F equals ma. Now, this is where it gets a little bit weird. We have to go back to chapter 2 in kinematic formulas and look at this formula. Okay, remember that formula? Vf squared equals Vf squared plus 2ax. If I am only moving in one dimension, and I don't care about negative or positive because with work we'll see that comes to play a role later. If I'm only moving in one dimension, d and x are the same. Again, one direction, one dimension, d and x are the same. X is displacement. If I move from here to here, my displacement might be 2 feet. The distance would still be 2 feet. Okay, again, I'm assuming I'm only moving in one direction and in one dimension. It's a big assumption to make, obviously. So if the case is true that x and d are the same, what's interesting is that you have ax here, really. This is really like ax. And what is here? Ax. So solve for ax in this formula, which is kind of different, right? You usually solve for one variable, don't you? So I want you to move this over and then get rid of the 2. So you get ax by itself. So how do you move this over? What operation? Subtract it. So we get Vf squared minus Vi squared equals 2ax. And then how do I get x by itself? How do I get rid of the 2? What do? Divide. Divide by 2. And there's ax right there. So this expression, Vf squared minus Vi squared over 2, can replace AD in this other formula over here. Let me point that out so you can see it. This right here is really mass times AD. But since D and X are the same in this problem, I could replace that with an X. Again, mass times A times V, mass times A times X. Same thing in this case. Displacement and distance traveled are the same for one-dimensional motion here. So I replace AX now with this entire expression. Get rid of AX on the next line and replace it with this expression. Don't worry about the derivation as much as the final answer we're going to get to. That's what you're going to end up using. I'm just showing you where it comes from right now. What does this look like from the last slide, or 2 slides ago? Anybody pick up on it? It's not obvious, that's why. When you have a coefficient out in front, right? And inside of the parentheses there's a sum or a difference. What do you have to do with that coefficient? What's the word?
Not multiply, divide it. Like all the factors have to be divided by the one that's, or multiplied by the one.
Yeah, what's the word for that? Distribute. You need to distribute, right? So the mass gets distributed to the numerator in both spots. The 2 can actually go like this, really, if you want to. The 2 could go over here, and you don't need it right there, actually. You can move it, it doesn't matter. Because the 2 is really just dividing both. So if I put the 2 here as division or here, it makes no difference.
And the next one, it looks like 1/2 mv squared.
Yeah, this is kinetic energy. Final minus initial. That's all it is. Distribute the m over 2 to both. So take this m over 2 and distribute it to both of these. That's what you'll end up getting. M over 2 Vf squared. M over 2 Vi squared. M over 2, that's just half. This is kinetic energy. That's all this is. Really, what this formula is telling us is the following. The work done on an object is 1/2 mvf squared, or kinetic energy final, minus 1/2 mvi squared, or kinetic energy initial. That's the work kinetic energy theorem at the end. All the derivation, honestly, you're not going to ever have to repeat. At least you're not going to have to repeat it here. But the idea that you can transfer from work into a whole other formula using an old kinematic, I want you to just see that that's possible. That's all. This in the box at the end is what's important. Actually, the previous line is really important. Okay, the way it's written, though, in textbooks and other sources, it's written like this, even though this is probably the more useful way you're going to write it. Gabe.
That is m divided by 2.
Over here?
Yeah, like why
So there was a 2 here, wasn't there?
Yeah.
So if I multiply 2 things, what's m really over before I move this 2? What was m over?
1.
And if I think about m over 1 times something over 2, don't you multiply the bottoms? So really, if I multiply 1 times 2, I end up with 2. Whether it's here or here, it doesn't really matter. Remember, this was over 2 initially?
Yeah.
I just moved it over here, but it makes no difference either way. In the end, it's the same thing. Okay, if I take, 5 times 1/2, or 5/2 times 1, the 2 doesn't matter whether it's under the 5 or the 1. Yeah.
What does it say? What is it in the one
1/2 mvf squared minus 1/2 mvi squared. So this is final and this is initial. That's all it is. So these are your kinetic energies. That's all they are. Now, why would you have 2 types of kinetic energy for one object? What is it doing?
What's next to the at the bottom?
F
Yeah.
and I.
All right.
Final and initial. Final and initial. So my question is, why are there 2 parts of the kinetic energy? Why is there final energy and initial energy? Think about when you do work to an object. What is it doing to the object? Yeah. You're either speeding it up or... So it's got a final energy and initial energy, always. So when you want to think about what does the work you apply do to the object, let's say this desk is at rest, and I push it, and I do, 25 joules of work on it. I could take that 25 joules and say, if it wasn't moving at first, the initial energy is 0, I could drop this off, and then solve for the final velocity. So this is another way to determine the amount of velocity change in an object instead of using old school kinematic methods. It's actually a lot easier, and a lot of students find this to be a lot easier. And you're going to see this with projectiles. We can actually solve a lot of projectile motion problems with energy also. So when it comes to the midterm, and you're given a problem, you could use either way. If you're better with projectile motion, with those old school formulas, X and Y, use that method. If you're better at doing it this way, use this method. Okay, it's up to you to choose when it comes to the midterm. That's why I keep talking to you guys about how the midterm is a lot of material, because you're kind of taking everything at once. Okay? So let's use this theorem now. Let's use this theorem and take a look at an example of what we're doing with it. I love this example, and it's really lame, but whatever. And how many of you have done this before? You put new socks on, and they're like super slippery the first time you wear socks, like you don't even wash them yet? Okay, so it's funny, in the last class I was talking to engineers, and they told me I have an obsession with Tom Cruise. So I remember the previous examples used Tom Cruise. This is where it started, actually. This is where it all began. Have any of you ever seen Risky Business?
Yes.
You remember when he comes in sliding in socks and just boxers? This is where this example made me think of. That's honestly where the whole Tom Cruise thing came from. Anyway, so on a wood floor, you decide to slide around. You just put on a new pair of socks, very low kinetic energy, or very low kinetic friction. You run, you start to slide with an initial speed of 2 meters per second. The question is, how far will you move if the kinetic energy coefficient, or kinetic friction coefficient between your socks and the floor is very low, 0.1. Okay, it seems like it's really difficult, but it's not that bad. Okay, it's not that bad. Clearly, you're not given mass. So although mass is used in kinetic energy, it's going to drop off somewhere. You're not going to need the mass to solve this problem. But let's go through the steps one at a time. So first, the kinetic energy work theorem automatically tells me the beginning. What can I automatically drop off? Just reading the problem, what can I drop off? George.
The 1/2.
Kind of. I could factor that out. It's got to be in all three terms to drop off. There's something else that can drop off for a different reason, though. So George is right that they both have 1/2. You can factor it out, but there's no 1/2 on this side, George, so you can't drop them off. It's got to be in every term to drop off the 1/2.
The first term is 1/2 and VF squared equals VF 0.
Yeah. What is the problem asking you? How far will you slide before you what?
Stop.
When you stop, what's your velocity? So VF is 0, right? So this whole thing is 0. Good. So no, yeah, this is the initial velocity, which was given in the problem as 2 meters per second. Now, it looks like it's impossible to solve still because you're not given mass, right? There's no mass involved. So there's probably going to be an opportunity for mass to cancel. The question is, what do we write for work? What's the formula for work? Again, what was the formula for work? Okay? Now, let's keep talking about this for a second. Why is my answer on the right side negative if I don't see a negative on the left side? What's going to happen with the negative part?
Well, they don't look like they're negative.
Why? What's cosine going to be? Cosine of what angle?
0. So, or 1. So 180.
180. Why is the angle we use 180? What is causing this object to stop? What is doing work on this object? The friction from the floor. The friction from the floor. So this F here is really FF. So let's put that. Again, remember, and I have to really point this out because this was in your homework last night. This FD cosine theta, the value F, is always some force. Well, what force is it in this problem? In this problem, it's friction. Friction is causing it to slow down. Friction is doing work on the object on the socks. Jake.
Wouldn't you replace it with UF?
We're going to do that, yep, absolutely. So let's actually do that in the next step. Let's replace FF with mu FN. Okay?
So when two forces are pushing in the same direction, that's 0, and when this is the force pushing in the opposite, that's 180.
Correct. Very good. The angle you're talking about, right?
Yeah.
Mm-hmm. So our formula for FF is mu FN. This was from last chapter. This is one that you really should know because in this chapter we're going to do a lot with friction because friction decreases the amount of energy. And since we're on energy, we're going to use friction. So I really recommend that even if maybe last chapter you struggled with this, just remember this formula or remember, be ready to use it. Whenever you have FF, if you're given something about mu, because look, we're given mu in this problem. Right, here's mu up the top. There's mu right there. And there's VI. That's all we're given. We're given VI and mu. That's it. So clearly, something has to drop off. We're going to solve for D, because it says how far will you slide. So we're looking for D. Fn, we don't know. We're going to have to replace that with something. Who remembers from yesterday? What's Fn for an object that's only moving left to right? What's Fn always equal to?
0.
Nope. If you need to draw a free body diagram that could help you, Juliet. FG. Let's go ahead and draw that. So if I were to look at Tom Cruise and draw him as a point in space, what acts down is gravity. What acts up is the normal force. He's already moving, right? He's sliding already. So once he's already sliding, what's slowing him down? Friction. That's it. There's nothing pushing him forward. If something were pushing him forward, he would keep moving, wouldn't he? But he does this. He runs into the room and he just starts to like slide. And then he eventually stops. So friction is the only force opposing his motion. Vertically, nothing's happening. He's not jumping. He's not crouching. He's just sliding left to right. That's all that's happening. Have you ever seen, there's a workout Olympians do, where they like go like this and they like slide back and forth? What's the word for it? Anybody know? It's a workout where you're on like a little track. A lot of skaters use it to practice for skating and stuff, because when you skate out each step. It's like a workout where you go left. Anyway, that's what this would be the equivalent.
Isn't that the Heisman? Isn't that what it's called? It's like
Well, the Heisman, he does this, I know, it's like the mode. But I'm saying like there's an actual workout. It's like an old school aerobic workout that like women in the 60s used to do with those home videos. You ever see those old home videos, like step-ups and stuff? There were like these videos that like, I don't know, you know what I'm talking about, right? Aerobic videos? And they used to like slide back and forth. That's what this is.
Yes, it's part of my mom.
Anyhow, doesn't matter. So, if Fn is balanced with Fg, we can replace it with Fg. But what's Fg? What's the formula for Fg? Mg. Fg equals mg. So replace Fn with mg. Replace Fn with mg. So I'm doing a lot with variables here because there's not really any numbers I can use. So I have to do that. Why does that make it very convenient? You have a question? Yeah.
I don't know why you use MG because you don't have
Well, I'm glad you said that, Jake. You don't have the mass. But what do you notice now? Mass is on what? So what can happen? That's the reason this works out nicely. Mass cancels on both sides of the equation. Why can I do that? Who can explain? How come I'm allowed to cancel mass on both sides? Because a lot of people are still confused with this. Why am I allowed to cancel mass? Not I can do it, but why?
Is it because, not that, I guess maybe they're both equal to each other since.
Well, yeah, they're definitely equal to each other, but mathematically, George. Why can I cancel m?
Separated by an equal sign?
Okay, agreed. It's separated by an equal sign, but what's the only operation occurring on both sides? Multiplication. Well, you're dividing both sides by m, yes. But if there was a plus sign, you'd have a problem, wouldn't you? If this was a plus right here for some reason, you'd have to have m, and then all three would cancel if this was a plus sign. This is all multiplication the whole way through. This is all multiplication the whole way through. So you can cancel m on both sides. It's like you're dividing both sides by m. Yielding a final equation of this. All of these things are known. Everything is known in this part. Okay? All you got to do is solve for d. Plug in. Mu was given in the problem. What was mu given as? 0.1. So, by the way, you could plug in or solve for d. Whichever way you'd like to approach this at this point. Plugging in, you get 0.1, 9.81, times d, times the cosine of 180. I know it's 180 because it's friction that's doing the work. Equals negative 1/2. And the velocity was given as 2 meters per second. And then solve for d. Again, for those that find that they like to use variables, please solve this previous line right here for d. Solve this algebraically for d. How far does this person slide? How far does this person slide? What do we got? What do we got? What's an answer here?
2.04.
2.04 approximately?
Yeah.
That's what I got when I did it. So just check your work. 2.04. And the unit is meters. Very good. Remember, cosine 80 is just -1. That cancels the negative here. A half of 4 is 2. So it's really just 2 divided by the product of 0.1 and 9.81, which is just 0.981. So 2 over 0.981. Okay, 2.04 meters. 2.04 meters is about 6 feet. This is a reasonable answer. Right? Think about it. If you ran on socks on a floor that's wooden and you just started sliding, you might slide a good like 2 or 3, 4 feet. This is about 6 feet or so. Okay, so you'd have to have a good enough velocity to get yourself moving, and these socks need to be very slick or very low friction for you to go further. What if you wore, here, follow-up question. How does the problem change if you wore those socks with the little feelies on the bottom? You know what I'm talking about? You were a kid, your parents gave you those socks with the rubber on the bottom so you didn't fall all over the place? That's why they're actually made. What would happen instead? How would this problem change?
Less.
Yeah, you would slide much less, right? What would increase? Yeah, the mu, the FF, overall friction, right? So instead of 0.1, you put those little rubber feelies on, now this is like 0.3. If this is 0.3, and you divide now by 0.3, you're dividing by a bigger number, it would make this division, or this distance, a lower answer. So the more friction on the socks, the shorter the distance traveled. That's why I like to solve algebraically, so you can physically see this. Karen?
Like, it's just like a new pair of socks, and they have more friction on the floor. And then,
Well, remember, friction is between two surfaces, so it's not just the socks. It's the interaction between the socks and the floor. So new socks on a floor versus socks with the rubber feelies on a floor. The floor is the same. The floor is not changing. So it's the socks that are causing the change in the mu value. Okay? New socks have a very low friction, and the floor itself, if it's like a stained wooden floor, would be very slippery, right? So there'd be very low friction. If you change the socks, you're now not changing the floor at all. You're changing the interaction between you and the floor. Nick?
When solving it at the end, you said you cancel one. How do you cancel one out?
Well, I just did this. I said, okay, there's 2 squared is 4. Half of 4 is just 2. So I simplified the right-hand side. Let me show you something else, though. I want you to see this physically. If I were to solve this equation algebraically, my answer would be the following. I'm gonna make this -1 so that my negatives cancel. So those are gone. So if I were to solve this algebraically, it would be d equals 1/2 vi squared over mu g. That would be my answer for d algebraically. So can you guys see that the distance you would slide is inversely related to the friction? See how this makes sense? Think back to inverse variation and direct variation. These are inversely related, right? Or indirectly related. If mu, or the friction, goes up, what happens to d? What does inversely mean? It goes inversely. It goes down. So think about the other socks. This is what I'm getting at here. If you put on a different pair of socks with those rubber feelies on the bottom, it's going to make this number, mu, larger. If this gets larger, your value of d gets smaller. These are indirectly related. Okay, these are indirectly related to each other. So with the variable formula, it's very easy to see that. When you plug in numbers, it's not as obvious, right? You plug in numbers, you don't know. Well, what if I change this? How is it going to change the answer? You'd have to plug in all new numbers and change this and see how the answer changes. By solving algebraically, I can see the relationship that exists. I can see that if I have more friction, I have less distance. And that makes sense. You wouldn't slide as far on a floor if there was a lot of friction. You wouldn't go far. If there was very little friction, you'd go much further. So it's good to see how they're related. How about velocity and distance? How are they related? How are velocity and distance related? Directly. So more velocity? Does that make sense too? Think about it. If you're doing this, and you go to slide, did I go anywhere? No velocity. If I run really fast, and then I at the same time do this and I have very low friction, I would slide a lot further because my velocity would be a lot greater. So do you see why in the beginning of the year I kept bugging you and saying like solving algebraically is very powerful? I mean powerful as in like you can understand what's happening in the problem just by looking at the position of the variables. This is the numerator, so it means it's going to affect it more positively or directly. This is the denominator, it's going to affect it indirectly. Okay, the algebraic solution is very powerful because you can see what happens to your answer as your parameters or variables change. Okay, but again, I'm going into a long spiel right now. What you need to know for the test for sure is being able to get to the answer. I might ask you a follow-up question like this saying, what would have happened if there were more friction? Would it go as far or would it go less? What would happen? You might know logically and you can answer, and that's fine. But this might help you also along the way. Okay, so if you ever want to solve algebraically, practice it on your homework. So that's where you want to practice that. Okay, practice solving algebraically on your homework, get an answer, and then maybe you do the problem over, or just do it over and plug in here and see if you get the same answer. That's how you can check if your algebraic solution is right. If I plug in VI, mu, and G, I'll get 2.04. So clearly my algebraic solution is right. That's how you can practice this with homework.
So we will have a question of really have to substitute something like mg for f, right?
You say again?
So you know how we substituted like mg
For Fn.
because it's equivalent essentially? Will we have a problem where we'll need
Sure, yeah, absolutely. That's why I'm saying that, like, for this chapter, the stuff from last chapter is going to play a role. Like, you need to know that friction equals mu Fn. You need to know that Fn is bound with Fg. And Fg is really mg. That's where all that came about. So practicing a problem like this is very useful. You're going to see something like this. But in general, you should be able to relate the last topic to this one. Okay? What I'm saying is that I'm not going to ask you to provide a generic solution like this. I'm going to allow you to plug in whatever you want. I don't care. Okay, but if you decide next year you want to challenge yourself and take AP Physics, this is the kind of answer you give. And then the follow-up parts, B and C, say, well, what happens if the mu value changes? What happens to your answer? This is how you can tell. No numbers are given. It just says suddenly, there's a new surface and mu has increased. What happens to your distance traveled? Decreases, because they're indirectly related. Yesterday, we ended by talking about what kind of motion, or what kind of, I shouldn't say that, what kind of energy. What kind of energy were we looking at? Kinetic, energy of motion. That's why I kind of gave that away. So here we're not going to look at the energy of motion anymore, but the energy of a state of being. So if you've ever heard the saying, or if somebody's ever told you have a lot of potential, it means you have a lot that you can do, right? You can do a lot of work, you can do a lot of good things, or you can, you have a lot of opportunity for more. That's what potential energy is really. So when an object has potential energy, it currently isn't really like using that energy, but it has the potential to use that energy in a form of like maybe say kinetic energy. So for this example here, we're seeing potential energy specifically gravitationally. That's the one that we're focused on. And that idea is very simple and it's obvious and you've seen it. The reason for gravitational potential energy is because of gravity. So when an object is at a position above ground level, it has the potential to do what when I let go? Yeah, drop, fall, move. So the idea is that when an object is at a certain height, the easy way to think about it is it potentially can have kinetic energy in a moment. It can convert from potential to kinetic by falling. So height gives it more or less energy. Now, how do you think it's related? Is height directly or indirectly related to potential energy? Directly. And think about it logically. If you were to stand on this chair right here and just step off of the chair real quick, you're not falling very far. But if you stood on something this high, when you landed, what would you do? What would you naturally do when you land? Would you land like this? How would you land? What would you do? You jump off something like this tall. Bend your knees. How would you bend your knees? What would that do? Absorb the impact. Because you have a lot of what? Because you're at a high height, you have a lot of energy. The higher the height you start at, the more energy you have when you land. What kind of energy when you land? We're going to see this in the next section, mainly, but the idea of potential energy converting into kinetic energy. Because as you move from a higher height to a lower height, you have to change energy somehow. So your potential energy at this height has to somehow change to something else. So what we think about is we recognize that as an object increases or decreases height, its potential energy changes. The formula we're going to use is mgy. What do you think y stands for again? Yeah, the vertical displacement. Okay, vertical displacement. So let's say, for example here, and let's assume these are, that B is the midpoint of AC. Okay, B is the midpoint of AC. So if an object moves from here to here, it gains a certain amount of energy. If it then, so this object, say a person climbs up the wall, gets to here, they gain X amount of energy. And then they, not X, but some number amount of energy. And then they continue up to the next level. How much energy they have compared to here? Double the potential energy. You double the height, you double the potential energy. If you triple the height, you triple the potential energy. Because again, potential energy and height are directly related. Again, y is the displacement, but you could think of it as height. If you start at the ground, you have no potential energy. As soon as you climb in elevation, you gain potential energy. Okay? You gain potential energy. Part of this topic is a little bit tricky simply because what you consider the ground can change based on your frame of reference. So in this room, what do we consider the ground? What's the ground in this room? Where is it? Point to it. It's right there, right? But if you were outside in the street, ground level would be the street. But if you were somewhere on a mountain, Mount Everest, and you were near, like, say, the three-quarters of the way up Mount Everest, and you stopped and you're walking on flat ground, you might consider that to be the ground because you're still climbing higher. So what we call a zero reference line can move. In this problem, I would consider C to be the zero reference line because it's the bottom of the possibility of this object to move. It can't go any lower, assuming this is a building, and if a building is there, a building must be on the ground. Okay? The building, unless the building extended, but it's not in the diagram. So level C would be considered ground level to me in this problem. I would not consider the top of the building as ground level because I can't continue to move up there. So the ground level location can change based on the problem. So we're going to look at this in a moment and see how that context changes depending upon what we're looking at. All right? So M for mass, G for gravity, Y for change in vertical displacement or height. My units of joules, again, as yesterday, do work out, and you can check those. You'd have kilogram times meter per second squared times meter, which would be kilogram meters squared per second squared, and that's what a joule was the other day. But again, this is another type of energy. So we have work that gives you kinetic energy, or work that can reduce your kinetic energy, like work done by friction. And now we have energy as a function of a state of being. Another type of potential energy, and you learn about this in chemistry, is the energy between bonds. When you learn in chemistry, when molecules split apart, what did they do? When a molecule would break into two pieces, what did it always release or give off? Always gave off energy, because there was energy stored in those bonds. So when you're able to break apart an element, the energy that's there has to go somewhere. And we're going to learn about this in the next section because of what's called conservation. Energy can't be created nor destroyed. It's always there, but it just changes forms. So in this case, we're seeing that we can have potential energy, but as the object starts to move, it can then be converted to kinetic energy. So let's look at this example. Jack, you want to read for us?
A 40-kilogram object is raised from the bottom of a well using a pulley system. The depth of the well is 25 meters, and the object is raised 3 meters above the rim of the wall. Determine the change in potential energy of the object. Question mark?
Yeah, there's no question mark there. Thanks, Jack. You're right. Go ahead and draw yourself a quick diagram of this. Think about what it would look like. Just draw a figure. Doesn't have to be perfectly artistic. That's the only given I'm going to list for now. Once I draw a figure, I can maybe write the other given out, because it looks like we're given two other pieces of information. So does your well look exactly the same as mine? If it doesn't matter. Again, it doesn't matter. It's all about reference lines. So I'm drawing the ground outside of the well, and the well goes all the way this far deep. And now I'm going to draw where this bucket or whatever this is, right? Object is raised. So it's raised 3 meters above the rim of it. So it's raised to pretty much up here. The depth of the well is 25 meters, and it's raised 3 meters above, maybe with a pulley crank system. And the question is, how much change is there in the potential energy of the object? So this is the kind of problem I'm talking about now. What is ground level in this problem? Because clearly I see the ground, right? And I did it on purpose. But that's not ground level. Where does it all begin in this problem? The bottom of the well. Call the bottom of the well the ground. And it sounds weird to think about this, but if you do that, it makes life easy. Because if you call this the ground level, and this is how we denote ground level, it's called the potential energy reference line. You put a P equals 0 at the bottom always, to say that this is where the object has no potential at the very bottom. So as far as you can go in depth. That's the ground level. Now, as a result, how far up has this object traveled to its new height? What is the distance traveled vertically? What is that? What is it? 28 meters. 28 meters it has traveled up. Because it's traveled 25 meters the length of the well, and then another 3 meters beyond. It makes life a lot easier when you make the reference line a certain spot. Now, if I had made the reference line right here, that probably wouldn't help me much because I don't know what this dimension is, right? Is the dimension where the ground is with respect to the well given in the problem? No. I know the well is 25 meters from the lip of the well down to the bottom. I know that here the ground is here, but how far is this? I don't really know. So it's not worth making the ground level the zero line because we don't know what this dimension is. If you wanted to, if you really wanted to and you wanted to do this, you could have made this ground level right here. And you could have said, well, it starts with a potential energy that's 25 meters below, so like a negative one, and then it goes up to one that's above it and positive. But then you'd have to do final minus initial. It gets really messy. So I'm trying to teach you ways that make it a little simpler. So wherever the lowest point is, make that the zero reference line. And then we just calculate potential energy. Mass times gravity times 28. It's always going to be the same approach as far as the formula is concerned. It's always going to be mgy, and y is always going to be the change in height. I always consider the lowest part of any problem to be the zero reference line. It will make life really easy, especially in the next section. So if you read your book, because I know some of you like to read through the section to help you understand and be a little more clear, if they don't consider the lowest level the zero reference line, it's just an alternate approach. But I'm telling you now that this is the best approach for sure. Consider the bottom of any problem the zero reference line. What do you get for an answer here? What do you get when you multiply these three? Then you go, what do you got?
10,987.2.
10,987? Okay, 0.2. So a lot of energy due to height. A lot of energy, especially when we consider comparing that to yesterday with kinetic energy. Okay, I want to get to one that's a little more complicated than this, but does anyone have a question first? The object starts at the bottom of the well. It moves 25 meters up. It then moves an additional 3 meters above the top of the well, moving a total distance of 28 meters vertically. God bless you. So its vertical displacement is 28 meters, and it is positive. What if it had moved down? What if I had lowered the object from the top to the bottom? Would it be, how would it change? Good. It would be negative because it would be doing what? Not gaining energy, but losing potential energy. As I move from this cliff or whatever and fall to the ground, I'm losing height. So I'm losing potential energy. Losing potential. But we've moved up in this problem, so we're gaining in this problem. Now, take a look at this one. Read through it on your own real quick and try to come up with some givens. This is the hardest part. So I want to make you have to challenge you a little bit here. The givens are not easy. So try to read this and list what you know. List what you know. You could draw a figure if you want to. And that'd be useful. Anybody want to take a stab at givens or give me a diagram they started with, what it looks like? You can even just hold your iPad up to show me the diagram or tell me what you think are your variables here. It's not an easy problem. That's why I'm having you try this one first. Yeah, go ahead.
I could be wrong with the variables, but I said for A, M is like 3.5 times M.
Okay, so at instant A, you're saying it's 3.5 M,
And then Y is 1/2 Y.
and Y is half of where it gets at the second level? And then what would the mass at instant B be then?
Like 1/2 M.
What would the mass be?
1/2 M.
1/2 MA?
First mass. It's like whatever you get for the first mass, what it uses.
It's not half the mass, because look what it does. It's carrying food, that's 3.5 times its mass, and then it's not carrying the food. It dropped it on the way up.
I'll just let it divide it.
Would it just be 10?
This would just be M for sure. There's one other correction I need to see.
4.5.
It should be 4.5 M, because it's in addition to its own mass. So it's really this. That's the mass at instant A. It's got the food, which is 3.5 times its own mass, plus its own mass. Then, at the second instant, it drops the food, leaving it only to be its own mass. This is tricky. If you had trouble with it, though, what should you have done? What could you always do? A little trick. Come on. I used M for mass. What could you have chosen for mass? X, or what else? A number. If you pick the mass to be 2, then it would be carrying 3.5 times that, which is 7. So this would be 2, and this would be 9. And that works also. The factor is still 4.5, because 9 over 2 is 4.5. So you could give the ant some mass, run through the whole problem with that mass as the given value. So if the mass of the ant was 1, the mass of the food was 3.5. 3.5 plus the mass of the ant, which is 1, would be 4.5. So you could pick a number, is what I'm saying there. Now for the height, you could do the same thing if you wanted to. But you're also told here that at instant A, the height is half of that of B. So I'm just going to call this one, if that's all right, I'm going to call this, oops, like that, okay? So I'm going to use a variable y to indicate height. But, I don't know, Atticus, give me a number from 0 to 20.
15.
All right, so the height is 15 at point B. So what's the height at point A? What's the height at point A? If the height at B is 15, the height at point A is 7.5. So pick numbers, it doesn't matter. You see what I'm trying to get at here? So the approach of a problem like this is that you're not given values, you're given parameters, you're given relationships. You're told that one location is double the height of the other. So give me a number, 10 and 5, 3 and 6, 2 and 4, whatever you want to choose, right? It's the factor of increase and change that's important here. That's what we're going to see at the end. It says by what factor? By what factor? So I'm going to continue with this approach with variables. If you want to pick numbers right now, put a number in here. Make this 1 or 2, whatever. Put a number, that same number you put a 2 here, put it here. Whatever you pick for y, put it here, put it here. That's fine. Whichever approach you want to take. So at instant A, its potential energy is mgy. The mass is 4.5 m, g is g, and y is 1/2 y. At instant B, it's again mgy. The mass is m, gravity is g, and the height is y. So the first instant is at instant B. It's carrying a lot of food, but it's at a lower height. In the second instant, it's carrying no food, but it's at a higher elevation. Which of these generates a greater potential energy? Well, in the second case, I have mgy. If you put numbers in, you can get numbers here, right? And get your number, please do that. But if you have variables, it's just mgy. What does case A simplify to be? I have 4.5, I have 1/2. What's 1/2 of 4.5? What is it? 2.25. In my variables, those tag on. Those don't disappear. So here's my potential energy at A. Here's my potential energy at B. Which is greater? Which is greater, mgy or mgy times 2.25? Yeah, it's clearly this one, right? Anytime you multiply something by any number greater than 1, it's going to increase. It's just a simple law of multiplication, right? So what's the factor of increase? Well, it's kind of right there for you. What's the factor of increase of part A compared to B, Trooper? 2.25. That's how much it goes up by. Factor means how does one thing differ from the other by multiplication. Well, at point B, you have a given energy. At point A, it's 2.25 times that much energy. Did anybody put in numbers? Nobody did? I was kind of hoping somebody would do that. Okay. If you try it though and put in numbers, pick a number for N, for Y, for G, you get an answer. And then if you take this answer and divide it by this answer, you'll get 2.25. A factor of increase is what does this number have to be multiplied to get to this number. So to find your factor, take the bigger number and divide it by the smaller number. You see what I'm saying right now? I feel like I'm seeing empty looks right now. This is something that a lot of students in this class and last year, the year before, struggled with, the concept of factor of increase. So let's say, for example, this number had turned out to be 10. What would this energy have been? If this answer was 10, what would this energy at point A have been?
22.5.
Very good, Gus. He knows that because he literally just took 2.25 and multiplied it by 10. So if you take these numbers now, so let's say I plugged in numbers for mass and for y, and I got answers of 22.5 and 10. How would I find the factor of increase? Take 22.5 divided by 10. That's how you find a factor of increase. The question is asking, how do I get from here to here by multiplication? So just do the reverse, which is division, and you can get the factor of increase to go backwards. Remember that multiplication and division are inverse operations. Okay? Just to help you with that. Again, I'll push you to keep this in mind that you can always add numbers or use numbers in there instead of using variables if you like. It's up to you to choose when you're on the test. So the next type of potential energy we're going to talk about is a really simple type. How many girls around the room wearing hair ties right now? I see one, her hair's up. I see another with the bun. A hair tie, what is it? Physically. It's a stretchy band. It's elastic. It's a piece of elastic material. So this next type, you could just relate to a rubber band, a spring. And we talked about springs already, so we'll relate that to this. You can think of anything that can stretch or compress as elastic potential energy, not just springs though. We model everything with springs because springs are very easy to use to model things. But if you have a rubber band, you can think about a rubber band as having elastic potential energy. What about a slingshot? You pull back in a slingshot and you let go, the object moves. Why does it move? You're giving it energy. The energy that you put into the slingshot, you're storing energy, you release. What happens? All that energy gets converted to what kind of energy? Good, kinetic, because what does it start to do? It starts to move. So the energy you store in the spring or the slingshot when you let go, the object gets faster, 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 it releases, it shoots. So all the energy that was stored gets converted to kinetic and it gets launched away. Once it's no longer being pushed by the slingshot, it's got all kinetic energy. And then it'll start to fall, and then it'll lose potential energy also. So there's a lot going on with energy here. Anything that can stretch or compress can have elastic potential energy. K is a spring constant, and I want you guys to recognize that a rubber band has a K value. Your pen, the spring in it has a K value. The hair ties, K value. Anything that can stretch or compress has a K value. Is that clear? Understand what I'm saying? Because we already talked about this in terms of springs, but I want you to understand for all things that can be stretched, they can have stored energy. K, what were the units? Anybody remember the units from K? This was from earlier in the year with forces. Talked about it in, I think, 5.2 or 5.1. What were the units for K? It was a spring constant. Nobody remembers these units? It was newtons over meters. Remember, a spring constant was how many newtons of force it takes to stretch it 1 meter. Again, the K value is the strength of the spring or the elastic material. If it's something like a rubber band, that's got a very low K value. Does it take you much to stretch a rubber band at all? No. They're made to be flexible. That's the whole idea, right? It's the concept. But if you wanted to take, let's say, a piece of fishing line, this is just fishing line over here. If you want to take a piece of fishing line and stretch it, it's got a very high tensile strength. So it would stretch eventually very little, but it would have an extremely high K value. It would not be able to stretch very easily at all. So the K value indicates the strength of the thing that is stretching or compressing. So it's measured in newtons per meter because it takes a certain amount of force to stretch it a certain distance. X in this case, what did X represent? Remember Hooke's law? This was Hooke's law from the last chapter. Same variables again here. Same exact variables, K and X. What was X in this case? Anyone remember? Use logic if you have to. Think about the scenario. What do you think it could be? Come on, take a stab at it. Logic can only really lead you in one direction, I think. Distance of what? You're right, distance of what? Careful, not the object. Keep in mind, what are we looking at? We're looking at a spring. We're looking at a spring, not the object, the spring itself. How far it extends or compresses, stretches. Okay, yeah, X traditionally is distance traveled or displacement. In this case, we would use X to be. In the case of springs, X is how far it stretches or compresses. When we did Hooke's law with forces, if X was positive or negative, it mattered because it changed the sign. Does it matter anymore for this? If X is positive or negative, does it matter? Why not, Mike? You're going like this. You're right. Why not? Why doesn't it matter if X is positive or negative anymore? Look at the formula. It's squared. Thank you for the help. I didn't figure it out. It's squared. When you square a negative number, it's still positive, right? So if I take a spring and I compress it, I'm storing energy. I'm giving it energy to then push back. If I stretch it, I'm giving it energy to do what? Pull back. But I'm still storing energy. I'm giving energy to the system. I'm giving energy to the system. So let's look at an example of this. This is the diagram in case you're wondering. Okay, so X is the distance compressed. Traditionally, by the way, we call this the free length or relaxed length. So meaning the spring is attached to a wall, let's say, and that's where it normally sits under no forces. But as soon as you push on it and compress, maybe it moves to here now. So this is called the free length, or as you see here, the relaxed length. And then the other one would be the stretched or compressed length. But what matters is that we see here from here to here is the stretched or compressed length from end to end. I could also do where? Instead of end to end, where could I measure from? Come on, people, think about it. I measured from end of the object after it's been compressed, and then the end of the object before it was compressed. Where else can I measure and get the same length instead of the ends of the objects? Like? The beginnings. It's the same length, isn't it? Assume the object is the same because it's physically the same object. This is the first scenario. Then you take the same spring and just compress it. That's what you're seeing above here. So the compressed distance could be from front to front, from back to back. Where else? Where else? Inigo? Middle to middle. From middle to middle. I could also think of this as the length. From the middle of this one to the middle of this one. But no matter which way I measured this, those three line segments drawn are all the same length. They're all the same length. It doesn't matter where you measure from as long as you are consistent. Back to back, or front to front, or middle to middle. It doesn't matter which of them you choose. Okay, the idea is similar to potential energy reference line. I could call this the beginning and call this the end. Or this the beginning and this the end. Or this the beginning and this the end. Either way, it's the same distance or same compression distance in all three scenarios. So let's look at an example. A spring is compressed from its free length of 10 centimeters to a length of 4 centimeters. It's a really easy question. If the rigidity is given as 300 newtons per meter, how much energy is stored? I'm literally giving you each piece, and it's not meant to be challenging, it's meant to just practice. We're going to see more challenging stuff with this concept in 6.3. Draw yourself a diagram if you'd like to. You don't really need to, but if you want to, you can. Bless you. Traditionally, by the way, it is drawn from center to center. Okay, just so you see in textbooks, a lot of the time, they'll draw center to center. That diagram was front to front, but it doesn't matter. So that's how the spring started, right? Was it stretched? Was it compressed? What happened? It was compressed, right? And even if it did say compressed, how would you know it's compressed? How would you know it's compressed? What's the new length of the spring? 4, and 4 is less than 10. So now the spring has been pushed back. I'll draw it in blue. Now it's there. And now the length from here to here is 4. So you have to be careful of the wording. You're not given x in this problem. It's indirectly given, obviously. You can do subtraction. It's pretty simple. But you have to see the wording. It says it's compressed from a free length of 10, that's normal, to a length of 4. So you're given the new length. You're not given how much it's compressed by. How much is it compressed by? Not a factor, but a change. What's the change in length here? 6. Thank you. That's the change in length, 6 centimeters. Original was 10, the final is 4. The K value is given. Are my units going to match up? Am I good to go? Am I good to go? What do I have to do? Meters. The K value is newtons per meter. That should be an indicating factor that centimeters don't work here. It's got to be meters. It's got to be standard units. 6 centimeters is how much? Prefixes. 6 centimeters is how much? 0.06 meters. Centi means hundredth. So we know we're going to move 2 decimal spots. 1, 2. Okay, some of you still make these mistakes on tests. That's why I'm making point this out. Got to know our prefixes here. So the potential energy stored in any spring is given as 1/2 kx squared. So at this point, it's just arithmetic. It's going to be a very small amount of energy. This was compressed a very short distance. Think about it, 6 centimeters, right? That's like this far. So you're not compressing the spring a whole lot. And the rigidity of the spring is a low enough value. If the K value was like 3,000, like the shocks on a car that have much higher K values, you'd be storing or losing or dissipating a lot more energy. It's going to be 0.54 joules. Bell's going to ring in a moment, so I take a question, but quickly let me point out that at this point you should be able to do all these problems. So a lot of you started work yesterday, which was good. Tonight, finish it. Okay? Tonight, finish it.